Welcome to Pavinars, webinars for the pavement community. I'm Andrew Braham, and today we'll be talking about the development of master fracture curves for asphalt concrete. This work was based on a paper that Caleb Mudford and I published. And Caleb did some undergraduate research in this area of the development of master fracture curves for asphalt concrete. He obtained his Bachelor's of Science in Civil Engineering from the University of Arkansas in 2012, and you can find his LinkedIn profile here or in the comment section below. Before we get started on master fracture curves, let's talk a little bit about fracture testing fundamentals. Fracture is a way to try and quantify the cracking susceptibility of a material, and in our case specifically asphalt concrete. Fracture looks at both crack initiation and crack growth, and traditional outputs to fracture testing include fracture energy, stress intensity factor, J integral, and other measurements. There are several different ways we can capture fracture energy in the laboratory. One is by running a single edge notch beam fracture test. We also have the semicircular bend fracture test, and then finally the disc-shaped compact tension test. Recently there have been several developments with other testing geometries, but these are historically the three most common ways to capture fracture in the laboratory. Now you can see with all of these we have a load being applied in the SCB and the SCB. It's a 3-point bending load. In the DCT, it is a tensile pulling load, but we're also measuring a displacement. So there is an MTS gauge underneath the SEB and the SCB, and there is an epsilon gauge to the right of the DCT. And these are all measuring the crack opening. So we're measuring the load that's applied to the sample, and we're measuring the opening. And you can see here some examples of curves that we can collect when running fracture tests. And these load displacement curves are very common. Now, for example, we have two different materials here, an asphalt concrete that acts in a more brittle behavior. You can see this material has a higher peak load but a shorter displacement, whereas a ductile material has a lower peak load but a much larger displacement. And this is just one way that we can capture data while running a fracture test in the lab, are these load displacement curves. And we'll talk a little bit specifically about fracture energy, and this is how you calculate fracture energy. It's the sum, or it's the integral of the load over the displacement divided by the ligament. So here P equals the load, U is the displacement, and the A lig is the area of the ligament, which is the specimen thickness times the length of the crack. So again, if we take our load displacement curve, essentially the fracture energy is the area under this curve divided by the ligament, or the surface area that the crack creates in the sample. And typical units are, for fracture energy, joules per meter squared. Now, I personally believe that there are some disadvantages to traditional fracture energy reporting. For example, it only gives a single number. So two different curves can have the same fracture energy, but they can have very different shapes. They can have higher peak loads and smaller displacements, or lower peak loads and larger displacements, and your fracture energy would actually give you the same number. Another disadvantage to fracture energy is that it does not incorporate pre and post-peak behavior. So how quickly do you reach the peak load? And then what sort of curve do you have after the peak load? And we call that the crack propagation after and crack initiation before the peak load. Another potential disadvantage is you only incorporate a single testing temperature, and your fracture curves may look very different at different temperatures. So simply reporting a single number loses some of those shapes. So we were asking the question, how can we get more information? And different groups have looked at different areas. For example, you have the flexibility index from the University of Illinois that looks at the post-peak behavior of fracture, we decided to take a little different route, and we looked at master fracture curves. So how do we build these master fracture curves? Well, we build these master fracture curves by starting with our crack mouth opening displacement for our displacement portion, and then our load. So we have our load versus our CMOD. And you can see here we're testing at 3 different temperatures. And we're going to call these low, medium, and high temperatures. But for the data shown in this presentation, you'll notice that the so-called high temperature is still quite low. It is below ambient temperature by a significant amount. Regardless, we have these 3 curves. Now, if we were to take the fracture energy, you can see as the temperature decreases, the fracture energy also decreases. So we found this fracture energy by simply taking the area under those curves and dividing it by the ligament length. Now, in order to construct the master fracture curves, we first want to find the energy increments for each curve. So we're going to take this low, medium, and high testing temperature and find the energy increments for each curve. And we can see that right here. So for each unit of increase of CMOD, we have some sort of incremental gain of fracture energy at the 3 temperatures. Once we have these incremental energies, we want to find the cumulative energy at each temperature. So simply taking the sum of these curves, and you can see these are the cumulative energies at the 3 temperatures. So before, with the incremental energies, the minus 6 degrees Celsius had the highest incremental energy, so it makes sense that it would also have the highest cumulative energy. And you can see another interesting trend here is that as the temperature increases, the CMOD at the maximum cumulative energy also increases. Once we have these 3 cumulative energy curves, we shift 2 of the 3 sets of data. So we shift the minus 18 and the minus 6 data, and we simply shift the higher temperature to the right until they overlap with the lower temperature. So you can see the minus 30 degree diamond, the maximum cumulative energy now touches the minus 18 degrees Celsius curve. So we simply shifted until the minus 18 curve intersected with the minus 30 curve at the maximum cumulative energy. And this is how we developed our master fracture curve, by looking at these 3 temperatures in series. And once we've had these shifted temperatures, we can simply trim the bottom of the minus 18 and the minus 30, and we obtain our master fracture curve. And the nice thing about this is now we can compare the fracture behavior of asphalt concrete mixtures across the 3 testing temperatures during the entire fracture tests. In order to do this, we looked at the influence of air voids, aggregate type, and asphalt binder content. We tested 28 mixtures at 3 temperatures in a partial factorial design. So our testing temperatures were based on the low grade of the PG binder grade in each mixture, and we took that low grade, we subtracted 2 degrees Celsius, we added 10 degrees Celsius, which is the BBR temperature, and we added 22 degrees Celsius to that low grade. So for example, if we had a PG 64 minus 28, we tested at 2 degrees below the low binder testing grade, so minus 30, 10 degrees above, which is minus 18, and 22 degrees above, which is minus 6 degrees Celsius. And that's how we got our low, medium, and high testing temperature for each of the mixtures. We used the DCT, the dish shaped compact tension test configuration, and our air voids were 4% and 7% in our partial factorial design. We used a granite and limestone aggregate, and then for the asphalt binder content, we simply looked at the optimal asphalt binder content, and then we added 0.5%. So we just put 0.5% extra binder after performing the SuperPave mix design. And this allowed us to analyze the influence of air voids, aggregate type, and asphalt binder content on the master fracture curves. So let's start with the air voids. You can see here just two sets of master fracture curves, one with 4% air voids, one with 7% air voids, and everything else identical with the mixtures. And we fit a fourth degree polynomial. We found that was the most appropriate fitting function. And we felt that by using these master fracture curves, we were able to allow for a deeper analysis of fracture behavior. So here on the axes, we have the cumulative energy and we have the shifted CMOD on the x-axis. A nice thing about using these curves is we were able to establish lines of equality. So in theory, if the air voids had zero impact on the master fracture curves, all of these data points would line up exactly on the line of equality. But you can see that it appears that lower air voids have higher cumulative fracture energies. And we were not able to see this when we simply looked at a single point of fracture energy measurements. So this is some additional information, how these master fracture curves are lining up on top of or above the line of equality, which implies that having 4% air voids actually gives you a slightly higher increase of cumulative fracture energy. We could go through a similar exercise with limestone versus granite. And a trend that we saw here is that the cumulative fracture energies cross. So the high temperature behavior, which is those higher cumulative fracture energies, are actually the opposite behavior of the low temperature cumulative fracture energies. So at the beginning of this test, the limestone actually had a higher cumulative energy, so those are the lower testing temperatures. But then at some point, the granite actually jumped and then had the higher cumulative fracture energy at the higher testing temperatures. Now, the very interesting thing about this is with these master fracture curves, we can actually identify exactly when this transition occurs. And it occurs around 600 joules per meter squared. And this is quite interesting because when we look at all of the mixtures with our line of equality, we can see this is not an uncommon phenomena. Here you can see multiple mixtures that had both granite versus limestone aggregate with all the rest of the material identical. Multiple mixtures actually had this 600 joule per meter square crossing point, where you went from having a higher fracture energy with limestone aggregate to a higher fracture energy with the granite aggregate. So across the samples, 600 joules per meter squared appears to be some sort of transition point. And while we see this with aggregate, it also could be a function of the surface charge, a function of the binder adhesion, a function of binder absorption. There's a lot of different reasons this could be happening, but the fact that 600 seems to be an important number is quite interesting. And then finally, for the asphalt binder content, we found that the extra asphalt binder only influences the so-called high temperature behavior. The lines were almost right on top of each other for the low and mid testing temperature behavior. And we found that the effect of asphalt binder content was not as significant as air voids or aggregate types. And this really pops out with the line of equality. Most of the data falls on the line of equality, and that means that simply adding more asphalt binder does not seem to influence the cumulative energy significantly. So in conclusion, master fracture curves are a way to quickly identify significant temperature dependent deviations in cracking behavior. And while the fracture energy alone did not find a statistical difference in air voids at 4% versus 7%, the master fracture curves did show different trends, which is important and interesting. We found that 600 joules per meter squared for aggregate types may identify some sort of important cracking behavior or some sort of transition point in cracking behavior, which is quite interesting. And we also found that additional asphalt binder did not seem to enhance cracking resistance. So if you're interested in learning more, the full paper can be found in the link below and also here on the slide. It was published in the Journal of Materials and Civil Engineering, and there is the DOI number. Thank you very much.